In this video, we're going to look at an example of converting an iterated integral to spherical coordinates and then evaluating that new iterated integral. So we're being asked to show that the iterated integral from negative infinity to infinity for x, y, and z of root x squared plus y squared plus z squared times e to the negative quantity x squared plus y squared plus z squared is equal to 2 pi. Alright, so the limits of integration here are telling us that we're integrating all over three-dimensional space. If we were to do this in terms of rectangular coordinates, we would have three doubly improper integrals, right? Because we got a lower limit and an upper limit of integration for each of the three variables that are not good limits. So I would end up having to do several integrals trying to be able to compute this appropriately by doing limits appropriately. All right, so instead, let's convert this to spherical coordinates and see that we actually only end up with one improper integral. So if we're going to look at integrating over all of space, well, certainly the distance that we can get from the origin goes off to infinity. So our rho definitely has to go from 0 to infinity. But the other two variables in spherical coordinates don't have infinite limits of integration, because all we need to do is rotate around on the xy plane. That can be described as 0 less than or equal to theta less than or equal to 2 pi. And we just have to be able to come down from the positive z-axis downward toward the negative z-axis. Well, the only values you can get for phi out of that are from 0 to pi. So in spherical coordinates, notice that we're going to be able to express this with only one infinite limit versus 6 infinite limits. So when we convert this over to spherical, x squared plus y squared plus z squared is rho squared. So this square root quantity here becomes rho. And then we have x squared plus y squared plus z squared in the exponent. That becomes rho squared. So I've got rho e to the negative rho squared. The differential gets replaced with rho squared sine phi d rho d theta d phi. Here's your limits for rho. Here's your limits for theta. Here's limits for phi. Again, we have a product. Our integram can be written as a product of functions of single variables, so we can split our integrals up here, especially since we have constants here. So I can do this as a product of three integrals. The middle integral here is just 2 pi. The outer integral here, if we go through it, we'll get 2. So this just turns out to be 4 pi here. Our other limit, we need to be careful. We should do this with handle our improperness appropriately by looking at a limit. So replace it with a variable and let that variable go to infinity. First, we can do a u substitution to rewrite this equation. Let's let w equal rho squared, and then dw is 2 rho d rho. So I get a w e to the minus w dw is my integrand. And then, of course, if my upper limit is b, when I plug that in for rho, I get b squared. So my new upper limit is b squared. Then I can do this by parts, which is what I'm doing here. And by the time we get all the way down to here, this limit turns out to be 0. And then this limit, no matter what we put in here, if we put in 0 for w, we get 0. If we let b go to infinity, after we plug it in, this is going to go to 0 as well. So this entire term is going to go away. This, we put in 0, we get a 1. And then as b goes to infinity, this will go to 0. So this limit, all this entire limit goes to 1. So we just end up with an answer of 2 pi.